ahead and pick up where we left off yesterday, and we should finish the Algebra 2 material. Again, the nonlinear functions that tend to be covered on the SAT pretty consistently are quadratic functions and exponential functions, and then sometimes just some properties of polynomial functions and graphs of non-linear types of functions. All right, so let's look really quickly then at the exponential functions, what you need to be able to kind of pull from that. So here is your general form of an exponential function. Often it's based on time. And so the equation is going to be some value of 1 plus or minus r. R is generally going to be some rate of change as a decimal. And so if it's saying that it grows at 6%, it'll be 1 plus 0.06. If it decays, then that's a minus. So a decay would be subtracting. So if it decays by 6%, then that growth factor, this is called a growth factor here, or decay factor. It's growth factor if it's greater than 1, decay if it's less than 1. Right? And so that's kind of what you're looking for. The A value is your initial amount, and the initial amount means the amount at time 0, right? The amount that you start with. And so based on what you see, like just from that, and what you also recall, hopefully, from your work with exponential functions, see if you can answer that first question, please. All right, so I haven't specifically emphasized to the extent that I would, when you come across a question, scan the answer choices first. And that's pretty solid strategy for every question, because oftentimes the answer choice will give you a hint as to what you're looking for. So here what we see, just by looking at the answer choices, you see that it's an exponential function. And you can see here that you're trying to decide what is my initial amount, because the initial amounts change for all of them except for the last two. And then also, what's that growth factor? Okay? Because the growth factor is different for all but the first two. And so if you are kind of gauging that relationship here, you know that you're looking for growth or decay. You see increase by 6%. Right here, that's all you need to pull from the problem. If you scan the answer choices and you see which of these equations is the best fit, we know this is going to be a growth factor of 1 plus 0.06. Okay, where A, if you want to fill it out, A is this initial amount of 15,000. Okay, but you don't even need that, because when you look at the answer choices, you can see if you find the correct value for the parentheses, you have your answer, which would be option C. Okay, the one below is sort of the other. I'm going to talk through that as well. So like try 48 here really quickly as well, just because like it kind of demonstrates or points out the difference between growth and decay in recognizing and interpreting exponential functions. So once again, if you scan these answer choices, you see your initial amount is either 21 or 0.34. And then your growth factor is different for every single one of those, but it's an exponential form. So as long as you know your growth or decay factor, you have your answer. You don't need anything else. So when you see that it decreases by 34%, that means that we're taking 1 minus 0.34 to the t, or x in this case. But that just tells you right away. That's all you need to know. It is true that 21 is your initial amount, because you see here from the input, the value at time 0 means your initial amount is 21, so that's going to be that A value. But that's sort of the difference between growth and decay that you need to be able to identify. All right. This next one I'm also going to do both, because I want to talk through it, because again, this isn't something that specifically is the most intuitive. Okay, but a lot of times when you're working with the exponential functions, what you see here in the power is you see a fraction. Okay? So notice here it's basically thinking of this as 1 over 670t. That's the power here. And what that means is that this growth or decay factor, 2, or doubling, happens for every time unit, it happens 1/670th. And so what that's telling you is in order for this to happen one full time, t, this whole value would need to be a 1, which means what would t have to be for that doubling to occur? What would t have to be so this total amount in the power is 1? 670, right? It's whatever that denominator is. And so when you're looking here, how much time has to happen for this population to double? Well, this is telling you. This growth rate of doubling happens every 670 times, or time units. So your answer would be 670. All right. So I want you to try number 51. Again, this is something that not all of you have been exposed to yet, okay, but I want you to see how you would solve it, even if it's something that you haven't seen quite yet. Well, actually, before you do that, let me talk through the notes for this. So that way, if you haven't seen it, you will see. All right, so this is an example of those nonlinear functions that aren't quadratic, aren't exponential. Okay, and so this is based on some patterns that occur for all polynomial functions. Okay, and so a polynomial function has the following rules. If it has a positive leading coefficient and it's an odd degree, meaning the highest power of its x is an odd number, then the graph is going to go down and to the left. Something's going to happen in the middle. Again, it will vary depending on the power, but it'll go up and to the right. If that leading coefficient is negative, then that graph gets flipped, reflected, and so that switches. It goes up to the left and down to the right. If you have an even degree, then the left and right, the end behaviors are going to be consistent. If it's a positive leading coefficient, both of the end parts of your graph will face up or open up. And if it's an even degree but it has a negative leading coefficient, it opens down. So again, you don't really know. We're not saying what happens in between. There's other rules for that, but the end behavior looks like this. And there's one other set of rules that I want to talk about that has to do with a concept called multiplicity. And multiplicity means every time a polynomial function crosses the x-axis, there's a consistent relationship that happens with it. If it passes through, straight through, so notice on this one, it's just passing straight through. It's not curving and it's not bouncing off of that. This means there's a multiplicity of 1. So the factor of x minus a negative 4, so again, the factor that corresponds to that 0 at negative 4 is x plus 4. And the multiplicity of 1 means that the degree or the power of that factor is a 1. But if the graph bounces off of the x-axis, that now has a multiplicity of 2. And so that means that if we took this factor of x minus a negative 2, so x plus 2, that since the graph bounces off of the x-axis, that means it's going to have 2 of those factors. So it's going to be x plus 2 quantity squared. And then finally, this last example is if it snakes through, then it's going to have a multiplicity of 3. So see how that graph kind of curves, snakes through, and it can snake in either direction. Okay, but this would give you this factor. Now it's x minus 2, whatever that 0 is, and the power of this would be 3. So the multiplicities correspond to the power of those factors. All right, so based on that here, try that top equation. Are uncertain of this, you can just type each of those functions into the graphing calculator and see which one looks the most like the given graph. So that would be sort of an alternative to this. But it's relatively time consuming to type all 4 of them. Whereas if you can just look at this graph, the first thing you should notice is the graph opens down. That means that it's going to be an even degree. Or sorry, the graph opens in the same direction. So it's going to be even degree. The graph opens down, so it's going to be a negative leading coefficient. Okay, now, you see that the negative is in all of them, so that's not anything that's helpful. but it is an even degree. So what that means is when you add up the total powers of x, it has to be an even number. Okay? We see that there are 1, 2, 3 places where this graph crosses the x-axis. Each one of these corresponds to a 0 or a factor, x minus whatever that 0 is. So x minus a negative 3. Here, x minus 0, so just x. And here, x minus 7. And now if we use the multiplicity test, this passes right through, so a power of 1. This bounces, power of 2. This passes right through, power of 1. And so based on this, you now can see your answer. The x plus 3 to the first, so that's eliminated, that's eliminated, that's eliminated. Just with that, you can now confirm the others. X is squared, x minus 7 to the first. And so you have your value, your function. And so again, not everybody remembers or even gets to multiplicities. And so that's something that can come into play. All right. So one of the things that, that you're going to be asked to do is solve quadratic functions. Okay? Again, if you have your TID9, it's really useful to just use the solve feature and answer that. So you can do that as well. But we'll talk through this. I'll show you, again, how to do it by hand, by TID9, by Desmos. So go ahead and try both 53 and 55 here. The first question is one that you can solve by hand by factoring. It is factorable. There are 2 factors of 80 whose sum is negative 18. But for the sake of a question like both 53 and 54, when you see it written like that and you're just being asked to find the solution, truly the TID9 is probably the most efficient way to do it. If you go into this algebra, F2 algebra tab, choose the solve feature, and then just type the equation directly in. So x squared minus 18x plus 80 is equal to 0. Then use comma x to tell the calculator what you want it to solve for, close off the parentheses, and when you hit enter, it gives you your answers. 8 or 10, either of those would work. And you could choose either one of them. And now, if you were solving this by hand, you would recognize that you can factor it. And so if you do just write these as the factors, x minus 10, x minus 8 is equal to 0. Use the 0 product rule. Set each of those factors equal to 0. You would get 10 and 8. So that's also efficient. If you see it, now like the problem below, which we're not going to do here, but there is a video capture of it. I'll talk about where those are too, if you want to see it. But that one you can't factor by hand, or you can't put into these linear factors, and so like using TID9 for that would directly get your answer. So solving a problem, TID9 is very useful. We could also use Desmos for that. If we type this whole equation directly into Desmos, what we could do is we could zoom and we find our 2 intersections, just click on them. We see it's 8 and 10, and those also confirm our answers. Okay? So whichever one that you want to do. Now for this second problem, 55, in this one I would probably, because it has that unknown A, either solve by hand or solve by Desmos, because Desmos allows you to create that slider and just test some values for A. Hey, and so what I'm going to do first, again, this one I would always kind of look to see, can I solve by hand? And I recognize one thing that leads me to believe solving this by hand can be an easy process, but it's not a process that students generally recognize. And so I'm going to kind of talk through what I'm looking for, or what I see, and then how to work with that. Okay, so notice that I have this binomial x minus 23 on the right side of my equation. The left side didn't have parentheses, but it also has a binomial x minus 23. So rather than thinking about dividing both sides by x minus 23 and canceling those out, and then solving the resulting equation, Okay, think about moving everything to one side. Again, anytime you have a higher degree than a linear form, like this is a quadratic form, anytime you have that kind of form where you have the x squared on the right, just move everything to one side. Okay, so if I were to take this equation and subtract the whole quantity x minus 23 from the left, or from both sides of the equation, move it over. So here's what my right side was, and then I'm going to subtract this whole quantity x minus 23. Notice I didn't expand out and then combine like terms, which also you could do. But by keeping it in this form, because I recognize these were the same, what I can now do pretty easily is I can remove that as a common factor. So if I took out x minus 23 now, from this first group of terms, I'm left with x minus a. And from this second group of terms, I'm left with just the 1, right? The whole thing comes out. I need that placeholder 1 to represent that. And so these are my two factors. And if I set them equal to 0, I get x minus 23 equals 0, or x equals 23. Here I get x minus a minus 1 equals 0. And so x equals add a to both sides, add 1 to both sides. So here I get my two answers, 23 and a plus 1, 23, a plus 1. So 2 and 3 would be my solution. Okay, if you were using Desmos for this, again, if we kind of did the same thing, x minus 23, just type the equation that's given. Oops, they didn't have parentheses there, start. X minus 23 equals x minus a times x minus 23. So notice it didn't prompt me for that slider on a. Anytime you have a variable, just assign it a value. I will always say just a equals 1 to pull it up there. And then you can change it if you want. Okay, and so what we're looking at is we have these, we have in this graph here, we have this solution. We see 23 and we see 2, right? So 1, we know that 23 is correct, right? We see that as a solution right here. We also see 2 when a is 1. So what I'm going to do in my next line is I'm just going to put what a plus 1 is. So now I see a plus 1, and 23. Okay, so a plus 1 is one of these intersections. Let's see what happens when my slider changes. I still have 23. And now I have 4 is 4a plus 1. Yeah, so the two that work are a plus 1 and 23. Did 3 work? Is 3 a solution on this example here? No, just those two. And so you could just test it by looking visually, solving by using the graph. All right, on the next slide, see if you can answer 57, please. One of the other types of nonlinear functions that you need to be able to solve are absolute values and square roots, okay, radicals. So one of the unfortunate or fortunate things about the SAT is it's not about pride. It's about knowing how to get a high score. I mean, like, again, it's unfortunate that that's the case. Okay, but if you think that you have to show that you can do this problem by hand, you'll probably be able to, but it'll just take you like a good amount of time. They allow you to use the TI-89. A TI-89 is going to give you the answer immediately. And so what I would do on this, my first strategy is I'm just going to go solve it on my TI-89. So hit the F2 algebra tab, select solve, type the equation exactly as it appears. Again, by practicing using the calculator tools, you'll be prepared for it. So here, the one thing here when you are setting this up, notice when I type the square root, it comes with this parentheses. Well, I need to put a whole quantity squared inside. So I'm going to need to put another set of parentheses here where I have x minus 2. Close that parentheses and then square it, and then I close the entire square root. So I needed that extra set of parentheses in there. Set that equal to the square root of my next one. Notice I'm just closing it up with this. There's nothing being done to this binomial. So here I don't need an extra set of parentheses. I can just type 22 minus 11x, close that off, And when I need to identify that I want to solve for x, so comma x, close off the parentheses from the solve command. And when I do, I get my answers. 2 and -9 are my solutions. Now, it doesn't accept both because it's asking you for the smallest one. Smallest means furthest to the left on a number line, which is -9. And you could have done this exact same thing on Desmos. And so if we took this same equation right here, square root, same thing, put parentheses, x minus 2, quantity squared. Make sure you go out of the square roots. If I don't go out of it, the equal sign will be inside that root. So make sure the equal sign falls outside. Square root of 22 minus 11x. And when I zoom in, I see, oops. Actually on this one, it looks like it doesn't show you what the value is, but you can see clearly on the graph that it's -9. If you are solving this by hand, then what you would look to do is you could square both sides to get rid of your radical. So you get x minus 2 quantity squared equals 22 minus 11x. And then you have a couple choices here. You could expand what you have. If you expand what you're looking at here and then combine your like terms, you get x squared minus 4x plus 4 equals 22 minus 11x. Move everything to one side, so we would subtract 22 from both sides, add 11x to both sides. Oops. So we get x squared plus 7x minus 18. And then you can try solve by factoring. You get x plus 9 and x minus 2, giving you solutions of -9 and +2, your lowest one being the -9. All right. So those would be sort of your options for that. All right, so I'm going to talk through this first one, 59, and then have you try 60. So this is kind of like what we talked about the other day to try to determine, or that new type of question, and it's something that we don't cover. I've never seen it covered in any of our classes that I've taught here anyway. Okay, and that is this idea of using the discriminant to help solve a question involving a system of equations where a linear equation and a quadratic equation intersect. Okay, so notice here they gave you two equations. One's quadratic, the second one, and then the first one is a linear form. Okay, and notice that it says it intersects at exactly 1 point. Okay, and so what that means is the discriminant, if it intersects at exactly 1 point, the discriminant, b squared minus 4ac, has to be equal to 0. And so that's what you do to solve this question. Okay, so if we take our system, what we can do is we want to replace this y in the second equation with the value of y from the first equation. So if we took 4y equals c and solve for y, we get y is equal to c over 4, and we're going to plug that in for this y. Once you do that, in order for us to evaluate the discriminant, we need to put it in this form where everything is on one side of the equation set equal to 0. And so if we just move the c minus 4 over, if you want to work with a positive leaded coefficient, you can move everything to the left. But if I just leave it, the first two terms on the right as they are, and then I'm going to subtract c over 4 from both sides. So this is now the equation in this form. And I can now take my b squared minus 4ac. Since this intersects at exactly 1 point, it means that that has to be equal to 0. And so I can find c by plugging that in. Here's my b value, 3 squared minus 4 times my a value, -4, times my c value, which is -c over 4. Set that equal to 0. and then solve. Notice here my negative signs cancel, these 4's cancel. I get 3 squared, which is 9, minus 4c equals 0. Add 4c to both sides, divide by 4, and there is my answer, 9/4. Okay. So that's how this is, like, again, it's a problem that I had never really seen before. Okay, but it involves the discriminant, which we don't necessarily emphasize, but it does tell the story of how many solutions there are in a quadratic equation. All right, so I want you to try number 60 on your own. See if you can extend this out, and just be aware, this one also is just slightly more tricky than what I just did, but it's based on the same principles. All right. One of the types of questions that is being introduced into the SAT with this digital format are these questions where they're using the discriminant to help solve questions where it gives you systems that involve nonlinear equations, and it tells you that they have either one solution or no solutions. Those are usually the two cases. It can also be two solutions, but it's usually one or no solutions. And it relies on the discriminant. So again, the discriminant is taking a quadratic equation, setting it equal to 0, and the discriminant is the portion that's inside the square root when you solve or apply the quadratic formula. So it's the b squared minus 4ac. If b squared minus 4ac, the discriminant, is equal to 0, then you're dealing with a system that has one solution. If it's less than 0, then you have a solution with you have a system with no solutions. And then if it's a number greater than 0, then there's going to be two solutions. So it's the same thing that holds true for solving a quadratic equation. And so the process for these has been pretty consistent. And so this is the approach that you would take. So here, if you see that you have two equations, so notice here's a linear equation and here's a quadratic equation. So we're dealing with a system where these intersect at exactly one point. Exactly one point tells you that this relationship is going to hold true. b squared minus 4ac is going to equal 0. So that's what we will use to solve and find the value of c in this equation. So the process for solving this first involves rewriting everything in terms of one equation. So we want to replace this y with the equivalent of y here. So if we know that 4y is equal to c, if we know that 4y is equal to c, we can solve for y by dividing both sides by 4, and that's what we're going to plug in directly here. So c over 4 is equal to negative 4x squared plus 3x. And so now we're going to put that into this form. Move everything to one side. So we have 0 is equal to negative 4x squared plus 3x minus c over 4. So here's your a value, here's your b value, and this whole thing is your c value. So it's not just the letter c, c represents that constant. And so the final step to solving this is to now set it into this equation and solve. So our b value, we take 3 squared minus 4 times our a value, which is negative 4, times our c value is this whole quantity, negative c over 4, and that's all equal to 0. And when we solve for c in this resulting equation, we have our answer. So here a negative cancels, this 4 cancels with one of those 4's. I get 3 squared, which is 9, minus 4c is equal to 0. And when I solve, I can add 4c to both sides, divide by 9, and there is my answer, 9/4. Okay, and so this is the method for solving. The calculators aren't going to help unless you use them to do some of the calculating for you. All right, let's take a look at this other problem now where it's clear it's a system, a little more clear it's a system. You have a linear equation and a quadratic equation, and you're told that they intersect at exactly one point. So once again, it's that same relationship. We know that the b squared minus 4ac is going to equal 0. And so what we can do here is we can set these equivalent to each other. Just replace the y up here with the whole expression 3x plus a is equal to 5x squared minus 27x plus 49. And then we move everything to one side. So we're going to subtract a 3x from both sides, subtract an a from both sides. So when we subtract a 3x, we get negative 30x. And when we subtract an a, we get plus 49 minus a. So this whole quantity right here is your constant, your c value. So once again, we're looking at a, b, c. And so when we take our discriminant, we get b squared minus 4ac is equal to 0, where b is negative 30. Our a value was 5, and our c value was this whole expression 49 minus a, and that's all equal to 0. And so here when we solve negative 30 squared, is the same as 30 squared, so 900. And then if you take 4 times 5 times 49, you get minus 980 for our constants. Again, when we take this negative 20, distribute it through, and then negative 20 times a negative a is plus 20a equals 0. And so if we combine these, we get negative 80 plus 20a is equal to 0. Move the 80 over. We add 80 to both sides, divide by 20, and you get your a value to be 4. So the other way you could have solved this was to plug these two equations into Desmos. Including the a value. So again, before solving for a. And you do need to create a slider. And with this slider, really, we're only testing these 3 points to see which one works. So if a, or actually, we just run this slider until we see So if we haven't done any of this work to solve for a, what we could do is we could just use the slider to move that blue line until they intersect. And so if you kind of see at this point, we can zoom in to see when they're still not intersecting yet. Here we see they have an intersection, and it was So the other way to solve this, again, if we didn't do any of this work on the side, is we could just type our system in exactly as it appears. So there's the first equation, type in our second equation, 3x plus a. We don't know what a is, so we'll create a slider, and what we'll do is we'll move this around to see when these lines intersect. So as I move to the left, it gets further away. So let's zoom in to see when they actually intersect, and I keep sliding it. And what I see here is right there's the intersection. And so if I know that a is equal to 4, I can substitute that in. So what I can do, what you could have also done is you could have just entered in your equations exactly as they appear. There's our quadratic equation. Notice this next one, we don't know what A is, so we'll create a slider and we'll look to see. Well, we want these lines to intersect, so I do need to increase the value of A until they intersect. I'll go over here to see if I can view when that intersection happens. There it is. The intersection occurs when A is equal to 4. And so if I want to find the point that connects them, or the point of intersection of these, I have the equation y equals 3x plus 4. And so when I look at where do these intersect, I can see here now my line intersects the system, the red graph at 313. And so my x-coordinate is 3, and that would confirm that answer as well. What we want to do is we want to solve for x. So what we can now do is go back in and solve our system. Y equals 5x squared minus 27x plus 49. And we have a second equation, y equals 3x plus our a value, which we just found to be 4. And so if we zoom out and look for the intersection of these graphs, right here, we can find that this one single intersection, the x value is 3. Okay, and so that would be the answer to this question. You could have also done is you could have just entered in your equations exactly as they appear. There's our quadratic equation. Notice this next one, we don't know what A is, so we'll create a slider and we'll look to see. Well, we want these lines to intersect, so I do need to increase the value of A until they intersect. I'll go over here to see if I can view when that intersection happens. There it is. The intersection occurs when A is equal to 4. And so if I want to find the point that connects them, or I have the equation y equals 3x plus 4. And so when I look at where do these intersect, I can see here now my line intersects the system, the red graph at 313. And so my x-coordinate is 3, and that would confirm that answer as well.